Good morning. Okay. So. Is there any question on the topics of yesterday? Again, don't be shy. Okay. So, I'm starting the recording. I think you should see my slides. Okay. So, I don't see any question. Well, if there are no questions, I will go on. Yesterday, we finished with the definition and some information on the concept of pH. And this is, let's say, all regarding general chemistry for this course. Just for since right now we will go on with the organic chemistry, I want to go back a bit here to the periodic table and take a look at this part, the non-metallic elements. Since in organic chemistry, almost all compounds are composed of course, mainly carbon, which is here a non-metal, and also nitrogen here, oxygen here, phosphorus here, sulfur here, and sometimes some halogens, fluorine, chlorine, bromine, iodine. Okay, so almost everything in organic chemistry is a non-metal with electronegativity values quite close one to the other. Okay, so of course the molecules will be made up of atoms connected by covalent bonds. If you remember, when the electronegativity is similar between the different atoms, among the different atoms, bonds are covalent. I mean, of course, they will be polar covalent bonds because electronegativity is different, but they will be covalent nonetheless. So most compounds in organic chemistry will be covalent, let's say, molecules, including mostly covalent bonds. Of course, we will have also ions, organic molecules that can be ionized, but the bulk of the molecule, most of the molecule, will include covalent bonds, where electrons are shared between atoms, okay, between couples of atoms. Okay. Of course, organic chemistry is a very wide subject. Millions of different organic compounds have been synthesized and are known. So they are the most important probably the most important part of any toxicological inquiry. All organic compounds must contain carbon. The definition of organic compounds is molecules containing carbon, basically, okay? So if they contain just carbon and hydrogen, we talk about hydrocarbons. And if they also contain oxygen, of course, we talk about oxygen-containing organic compounds, nitrogen, sulfur. Organohalides means the molecules contains one or more halogens, chlorine, bromine, and so on. Phosphorus-containing compounds. Of course, nothing stops a molecule from containing phosphorus and oxygen, or oxygen, sulfur, and nitrogen, and so on and so forth. So one or more so-called heteroatoms. Hetero meaning atoms different from carbon and hydrogen. Here you can see a scheme including many important so-called functional groups. We will briefly take a look at some of them, but it is just to give a survey of the wide variety of compounds that can be observed and synthesized in organic chemistry. Here in red, with the red circles, we have hydrocarbons. Here, oxygen-containing compounds, halogens, other oxygen-containing compounds. In pink, nitrogen compounds, sulfur-containing compounds, and in this case, aromatic, which are a kind of hydrocarbons which are cyclic and with alternating double bonds. Yeah, this is some classification, but I think we can skip this. Okay, so the most basic, the most simple, let's say, organic compounds are hydrocarbons. There are three main classes of hydrocarbons: alkanes, alkenes, and alkynes. Alkanes have only single bonds between carbon atoms, here a single line. Alkenes contain at least one double bond, here in red, and alkynes contain at least one triple bond. Okay. Alkanes can also be called aliphatic hydrocarbons. Of course, an infinite variety of alkanes can be synthesized, but we can distinguish in three main classes. Linear or straight chain alkanes. This means that every carbon is connected to just two different carbons, or one if it is a terminal carbon. Or branched alkane, when some carbons are connected to more than two other carbons. Usually three, because if you have four carbons, you only can write one compound, unless, of course, you have a longer chain in one of the other spots. So three or four connected carbon connected to three or four other carbons. And cycloalkanes, when the bonds form a let's say a closed polygon. most or all alkanes are usually flammable. When they are small molecules, small alkanes are usually gaseous. And when the molecules becomes larger, they become liquid. And if the molecule is very, very large, they can also be solid. This is an example of a branched alkane here, 2-methylbutane, which is liquid. It is flammable, and it is found in gasoline. And it is also, unfortunately, also found as a pollutant in urban city air, urban air. Both carbon-carbon and carbon-hydrogen bonds are quite reactive. Are quite unreactive. The bond is quite strong. In order to create a new bond, we have to break down this bond. Okay, so we have to in some way to break down a part of the molecule. Okay, they can react mostly with alkanes and in the part of the carbon-hydrogen bond, which is the less stable between the two kinds of bonds, carbon-carbon and carbon-hydrogen. In particular, for toxicology, is quite important the fact that the chlorine molecule, which is a biatomic molecule, can undergo dissociation, a special kind of dissociation, which produces two free chlorine atoms. As you can see here from the dot, this is an electron. It is an unpaired electron, because chlorine is belongs to the 7th group, so it has 7 electrons in the valence shell. And so one of its electrons is unpaired. The other 6 are paired, 2, 4, 6, but the 7th one is unpaired. And when a molecule contains one or more unpaired electrons, it is called a radical. It is usually very, very unstable, and being unstable is very, very reactive. So the chlorine radical is, or free radical better, is very reactive and reacts in fact readily with the carbon-hydrogen bonds. In this way, of course, the organic molecules becomes a different molecule. Here we can see an example of reaction of chlorine radicals with an alkane, the simplest alkane, which is methane. In this case, we can see that the radical chlorine reacts with hydrogen, and hydrogen goes off the bond with its electron to react with chlorine to produce hydrochloric acid. So methane is left with another unpaired electron, which is of course very reactive, and this electron, this radical, can react in turn with another chlorine molecule. This is an atom, a radical atom. This is a molecule. And so this radical reacts with another chlorine molecule, producing a different compound, which is called chloromethane. And you can imagine that this is methane, but any other organic molecule in our body if it was an important molecule, if it was modified in this way, including a chlorine atom, would lose most of its biological activity. So this is a very, very dangerous reaction, also because at the end of the reaction, we have regenerated the starting chlorine radical, which is ready to react again. So this is a reaction that can go on indefinitely, chlorinating thousands and thousands and thousands of molecules. Okay, and you may imagine that since carbon-hydrogen bonds are present in almost or probably all organic molecules, this kind of reaction can happen and can change the structure of almost any organic molecules in our body, in animals' bodies, in plant bodies, and so on and so forth. Okay, so very, very fast and dangerous reaction. Alkenes contain at least one double bond, and the simplest alkene is ethylene. The final part of the molecule of the name of the molecule is modified if the alkene was ethane, the alkene becomes ethylene, and so on and so forth. Alkenes are more reactive than alkanes because they contain the second bond, and this bond can be broken without breaking up the molecule, without disturbing the, let's say, basic single bond, which remains, which is the most stable and remains. So the second bond is less stable, and thus it can react more easily. So alkenes are more reactive than alkanes. They are also, like alkanes, highly flammable and quite explosive, usually. Of course, nothing stops a molecule from having more than one double bond, okay? A molecule, complex molecules can have 10 or 12 double bonds and so on, okay? Alkanes have the possibility of reacting again with, for example, halogens. But in this case, as you can see, the full halogen molecule reacts with the alkene, producing a dehalogenated molecule. So, without the need to undergo radical formation, the halogen can directly react and modify the molecule in two different adjacent positions. But also in some particular conditions, for example, they can also react with water to produce hydrated alkanes. Of course, those molecules are no longer containing double bonds, okay, because the double bond has been broken to produce the two other bonds, and so only a single bond remains. In this case, we have created an alcohol. Here, COH group is the alcohol group. Okay, another toxicological reaction which can be interesting from a toxicological point of view is the addiction reaction, between an alkene and, for example, oxygen. This is a reaction that happens with air oxygen, which is, as you know, is transported to the body through the blood. In this case, this addiction reaction produces an epoxide. Epoxide is this cyclic structure containing an oxygen atom. And this structure is really unstable, because we have a circle with just three atoms. So these bonds are not their optimal geometry, which is a 6 terms cycle, and they tend to break quite easily. So this epoxide is really, really reactive, and it can again react with the biologically important molecules in the body. So, of course, this kind of reaction cannot happen with alkanes, and it is one of the most important factors that can explain alkene toxicity. Okay, because of course oxygen is quite common in biological tissues, and so many alkenes can form this kind of epoxide. And this kind of epoxide is really reactive and really toxic. So alkanes are more reactive and thus also, generally speaking, more toxic than alkanes. A particular kind of alkenes are aromatic hydrocarbons. Aromatic hydrocarbons are hydrocarbons forming a ring structure, usually most commonly a 6 terms cycle. Here we have 6 carbon atoms, and if we look, let's say, in reality to the molecule, we see that the molecule is planar. Okay, all the carbon atoms are on the same plane, and we have 2 electron clouds, two let's say circular electron clouds above and below the molecule plane. So this is not a simple case of having double bonds. The double bonds have to be conjugated, meaning alternating between double and single. But in aromatic hydrocarbons, the double bonds are not localized. They are spread all over the molecule. In this way, this is the spreading of the electrons in the molecule. So the electrons are not localized between 2 specific carbons, like here. Here we have the electrons that are shared between those 2 single carbons, not anywhere else in the molecule. Here we have 6 electrons which are shared all over the molecule in this way, in this cloud. So these electrons are very exposed to possible reaction because they are, let's say, outside the plane of the molecule. And they are being exposed, they are also quite reactive. So also aromatic hydrocarbons are quite reactive compounds that can produce toxic derivatives. In fact, we can find many toxic substances, pollutants and so on, that are aromatic compounds. They are quite frequent as pollutants. For example, benzene, which is the simplest aromatic hydrocarbon here, is highly toxic and is one of the few compounds that it is surely a human carcinogen. In particular, it can cause leukemia. But also, all the other aromatic compounds, in particular, those called polycyclic aromatic hydrocarbons, which is abbreviated PAH, they are characterized by this kind of structure. So it is called fused or condensed rings because, as you can see here, two or more rings share, let's say, a side, okay? So two or more carbons, not just one carbon, but two or more carbons. And these are the most frequent, PAHs are the most frequent pollutants or toxic pollutants produced by burning organic matters. When we burn something organic, carbons tend to arrange in this way, okay, in producing aromatic and condensed aromatic structures. So everywhere nowadays, you know that most energy is produced by burning oil or coal or gas and so on. And so, of course, you can imagine that this kind of compounds is found almost everywhere. Of course, central heatings in homes, also in cars, although all of these produce polycyclic aromatic hydrocarbons. Okay. Again, also in addition to benzene, also several PAHs are carcinogenic. Okay, so we will see in the following that it is not the molecule by itself, but it is a derivative of the molecules that it is formed within the body. So the molecule enters the body modifies it, and the modified molecule is toxic and carcinogenic. But we will see it in the following. We also have organo-oxygen compound, oxygen-containing organic compounds. We have a lot of different compounds. We have already seen before the epoxide group, okay, a three-member ring with one oxygen. But we have seen also the possibility of an alcohol, which contains the OH group. We've seen that, of course, epoxides are toxic, are really reactive and toxic. Alcohols are also toxic, less toxic than epoxide, but they are also toxic. Even ethanol, which we can drink in wine and other drinks, but it is also toxic because one can become intoxicated with ethanol. And a particular kind of alcohol is phenol, where the OH group is bonded to an aromatic ring. Again, also phenols are usually toxic. So you can see that many compounds can be highly toxic. Here we have a C double bond O group, which is called carbonyl group. So here, if the carbonyl group is at the end of the molecule, we have an aldehyde. This is the simplest aldehyde, formaldehyde. And it is widely used in glues and especially for furniture. if you have some wood furniture in your home, it is kept together by glue, and the glue contains formaldehyde. Nothing in our chemistry is able to keep together furniture like formaldehyde-based glue. Okay, so it is still very, very frequently used, but unfortunately, it releases formaldehyde, and formaldehyde is a toxic compound. Often our homes are polluted by formaldehyde, and we take in formaldehyde by staying at home, and going out would be much less toxic regarding formaldehyde. Maybe it is more toxic for other compounds, but it would be less toxic regarding formaldehyde, because in the open air, formaldehyde is degraded by sun rays, by electromagnetic radiation, and so it becomes harmless. But also many other aldehyde and ketones, the carbonyl group, when it is within the molecule, not at the end of the molecule, but in the middle of the molecule, it is a ketone group. Many aldehydes are quite toxic. Again, this is due to the fact that aldehydes are relatively reactive. They are not very stable, because the double bond, the double CO bond, is quite weak, and it can easily open to produce, for example, alcohols. This is another toxic aldehyde, acrolein. It can produce explosives, explosive peroxide. It is a very, very strong irritant of the bronchi and the lungs. It is used in lacrimant gas used by police, for example. Then we can have different organonitrogen compounds. The typical group of organonitrogen compounds is the amino group, where we have a single bond between carbon and nitrogen. This is an example. Methylamine. Again, this is flammable, and it is quite irritating. But we can have also different, for example, this is a compound containing two nitrogen atoms connected between them, and also oxygen. This is called an N-nitroso compound. This is the nitroso group, so N-nitroso compound. This is also carcinogen. Or we can have nitro groups, and nitro groups are typical of explosives. This is one of the most important explosive, trinitrotoluene, TNT. I think everyone has heard of it, and it can also is, of course, explosive, but it can also be toxic. It can cause hepatitis or anemia. So, as you can see, any kind of compound, any group in the right, or let's say wrong conditions, can be toxic. And we have organohalide compounds. We have seen before how they are formed from alkanes and alkenes. They can, of course, bond different kinds of organic molecules. So this is an alkane, this is an alkene, this is an aromatic, halogen and halo compound. Okay, so any kind of molecule can contain halogen. As we have seen before, halogens in organic molecules can produce high levels of toxicity. We will see in the following that many haloorganic compounds are quite toxic. Okay, I don't think this is very important right now. We will see in much greater detail in the following, but it is important to recall this, that a particular kind of haloorganic compounds called chlorofluorocarbons have been very important as gases for refrigerating, for freezers and similar, also conditioning, air conditioning. Of course, as the name says, they are hydrocarbons containing both chlorine and fluorine. As you can see here some example. As you can see here and here we have also bromochlorofluorocarbons. But in the case of CFCs used for refrigeration, for air conditioning, the halogens substitute all hydrogens in the molecules. So they are no more hydrocarbons because they're not hydro. All hydrogens have been substituted by chlorine and fluorine, and in some cases also by bromine. Okay, those gases are not toxic by themselves. Okay, they are have very direct toxicity, but as I think everyone knows, CFC are very dangerous for the ozone in the atmosphere, in the stratosphere in particular, which is a layer of our atmosphere that protects us and the whole environment from ultraviolet radiation from the sun. Okay, so those CFC have been banned in I think all the world because they can be very dangerous and polluting regarding the ozone layer in the atmosphere. But I will speak more about them in the following. Okay, this is just to give a brief survey of possible problems caused by halo compounds. We can also have sulfur in our molecules, in our organic molecules. The most important kind of compounds are thiols, where we have the SH sulfur hydrogen bond, okay, and the SH group, it is the thiol group. Also quite frequent is the sulfide group, but this is of course much more frequent, and it produces a very strong rotten eggs, or in some cases garlic odor, but rotten eggs is the typical smell of sulfur compounds, and in particular of thiols. Okay. So I think this is everything for, let's say, just a brief survey of the different kind of organic molecules that we can find in different parts in our bodies, in the environment, and so on. Just to have some info on what kind of organic compound we will find then in the following of our course, of our lessons. Okay, are there any questions? Nothing? Everything's clear, I think. Okay, if everything's clear, I think we can stop and continue in about 10 minutes. Okay? If there's any question, please write them down in the chat. Okay? See you later. Okay, I'm back. Sorry. Ready for the second part. Just a question. Yesterday I've seen, let's say, 14 or 15 people connected. Now I see 10 people. Someone knows the reason for this change? I mean, maybe yesterday someone was just looking at the lesson to understand if maybe it could be interesting for them, and today they didn't take the lesson, or maybe there's some different topic, different lessons that can be concomitant at the same time, and so not everyone is able to follow all my lessons.
Not that we know of.
Okay. Okay, thank you.
At least for the first year, I mean.
Okay. But I think that the second year should not have lessons at the same time, because we are at the second. Ecco. In fact. Okay. Okay, you are Erasmus students. In fact, it was a bit strange to have overlapping lessons. Okay, not a problem. Just my curiosity. Well, if there's no questions, no, I don't see anything in the chat. So we can go to the second main topic, which is biochemistry. So we have seen something on basic chemistry, and now on biochemistry, on how chemistry works within biological systems. Okay, So it is biochemistry. Of course, the basic unit of all living beings is the cell. All cells have the same basic.
Can you share the screen? Can you share the screen, please?
Of course, of course. As usual, I forgot. Okay, here it is. Thanks for the reminder. I was saying that all cells have the same basic structure, but for complex living beings, just like humans and most animals, we have a lot of different cells which can have also widely different structure and functions, but the basic structure is always the same. We have a cell membrane that encloses all the cell and also the small organelles within the cell. Each of these structures has a different small, let's say, smaller membrane that envelopes it. And the most important structures within the cells are probably the mitochondria, the ribosomes, the nucleus, and I think this all, because vacuoles, lysosomes, and Golgi bodies will not be included in our topics. I mean, they are of course very important, but less interesting for us in this course. This is called an eukaryotic cell because bacteria have a different kind of cell. It is called the prokaryotic cell. But we will not talk about bacteria right now. Okay, so the cell membrane is a fundamental part of our cell. The whole cell is enclosed within a cell membrane, and also the small organelles are enclosed by an independent, let's say, smaller membrane. The cell membrane is highly lipophilic. It's composed mainly of phospholipids, so it is lipids that contain also phosphorus, and they have this kind of structure. They have an hydrophilic head and an hydrophobic tail. So a small globular head and a long chain, a long tail that is hydrophobic. And so, since everything in our body is in contact with water or with some aqueous solvent, the cell membrane is auto-organized in this kind of structure. It is a double layer, okay, two different layers of phospholipids with the hydrophilic heads towards the water. This is, let's say, outside the cell, there's water. This is, let's say, inside the cell, water also. So the hydrophilic heads are towards the water. And in between, we have all the hydrophobic tails. So the bulk of our membrane is lipophilic, okay, highly lipophilic. And this is very important because only very lipophilic compounds can readily pass the membrane, since they are very strongly attracted by the hydrophobic bulk of the membrane, and then can go in the cell. So only hydrophobic compounds can, let's say, enter the cell by themselves, or let's say naturally, not naturally, that's not the right term, let's say automatically within the cell. Hydrophilic compounds can only enter the cell if there's some specific structure in the membrane that can take and transport that kind of molecules from the outer part to the inner part of the cell, okay? So lipophilic compounds are easily incorporated into the cell, while hydrophilic compounds need some kind of transporter. We will see in the following that a lot of different transporters are included into the membrane. They are usually proteins that have this specific function of transporting some compounds or some classes of compounds from the external part to the internal part of the cell. Of course, this means also that hydrophobic toxic compounds can disrupt the structure of the cell, because they can go within the membrane and stay there and disrupt the arrangement of all these tails, these hydrophobic tails, that should be, let's say, more or less packed, one next to the other, and extended all along their length. So if some hydrophobic compound goes between the chains, or here between the two layers, it can disrupt the properties of the membrane, and this, of course, is a very big problem, because the membrane is very important for all cells' function and for cell integrity. Okay, of course, if the membrane breaks down, the cell will die very, very fast. The nucleus is one of the most important structure within the cell, and it is enclosed within another membrane which has the same basic structure. It is different from the cell membrane, of course, but it has the same basic structure, the same double layer of phospholipids. And the nucleus has the main function of containing the DNA and to regulate the use of DNA by the cell. Okay, and of course, again, this is a very important function, because the DNA is the genetic information that, let's say, is the blueprint for producing almost everything that, everything that is produced within the cell. So if something damages the nucleus, the nuclear membrane, again, the cell will die, or, which is often quite worse, can become out of control. It can become, for example, a cancer cell. So the nucleus is very important, and it encloses the DNA needed to produce everything that is produced within the cell. The cytoplasm is not really a structure, but it is the liquid, the gel liquid that fills the interior of the cell. Let's say that the cytoplasm is everything that is not organelles. Okay, it is important, but it has no. It is not structured, strictly structured like the nucleus and the other organelles. So I think there's not much that I can say right now that is significant. Okay. Very important in the cells, are mitochondria. Again, as you can see here in the drawing, mitochondria have a membrane, which is of the same kind of all other organelles and of the cell, but they have two membranes, an outer membrane, which is here, of course, the most external one, and an inner membrane, which is this one. You can see here that it is very, very wrinkly. It is not an homogeneous surface, okay? And this is important because it is right in these wrinkles that the most important and the fundamental function of mitochondria happen, which is the generation of energy, okay? Within the cell, all or many or most reactions that happen in the cell need energy in order to happen, okay? And the cell so needs a way to produce energy in order to carry out its reaction. And mitochondria is exactly where this energy production happens. The most important reaction producing energy is this one, where we have an organic compound, in this case a sugar, glucose, which is the energetic, let's say, the most important, the most iconic energetic molecule. And this organic compound is oxidized by oxygen, of course, to carbon dioxide and water. And this oxidation reaction is coupled to the production of energy, or it is probably more correct, to the release of energy. Of course, energy is not produced in any way. You know that the energy is never destroyed or created, but only transformed. So the energy contained in the chemical bonds of, for example, sugar, is released by the oxidation of sugar to carbon dioxide. Okay, here we let's say, here we say oxidation, even if I previously say that purely oxidation reaction don't exist. Only redox reaction exists. Of course, this is true also here. This is a redox reaction, but the only part that it is really interesting for us, or in this moment is interesting for us, is the oxidation of glucose to carbon dioxide. But of course, at the same time, we have also the reduction, and reduction happens on the oxygen here, because oxygen is reduced from molecular oxygen to water. But the important part here is that glucose is oxidized, and the oxidation releases the energy contained in the chemical bonds of glucose. This energy then will be stored in the cell, ready to be used for any needs the cell has. Okay? This process, the production of energy, the release of energy through oxidation, is called cellular respiration, of course, to set it apart from the body respiration that happens only in the lungs, in the respiratory system. Okay, these are, let's say, the most important structure of the cell. We have another very important structure, which are ribosomes, but I will speak about them in the following. Okay, then we go in more detail in the chemical compounds. Now we have talked about the organelles, the big structures of the cell. Now we take a look at some important molecules, big molecules. They are called macromolecules in the cell functions. First, we take a look at proteins. Proteins are macromolecules, very large molecules, that are made up of single building blocks. They are polymers made up of monomers, and those monomers are called amino acids. And here you can see the basic structure of an amino acid, and you can see that it is called an amino acid because it contains an amino group and an acid group, so amino acid. I want to underscore that amino group is NH2 or NR, and with some other carbon chain. And the acid group is COOH, okay? Carboxylic group. So this is the basic structure. Every amino acid in our body, in our proteins, has this general structure. So one primary amino group means an amine bonded to just one carbon, one acidic group, one hydrogen, and a side chain, okay? The only part of the amino acids in our body that changes is this side chain. Of course, different side chains create different amino acids. Here we have 6 examples of amino acids. The most simple amino acid is glycine, here, where the side chain is just an hydrogen. But we can have also a methyl group, alanine, thiol group, cysteine, serine with an alcohol group, another amino group, an aromatic group, phenylalanine, and so on and so forth. Okay, all different amino acids. Okay, and in our body, in our proteins, we have about 20 different amino acids. Okay, this just to see if I forgot something. No, just to give you an idea of how big protein is. A single amino acid like glycine or alanine is has a weight of about 150, and since we take many of them and we link them together, the molecular weight, the molar weight of a protein can go from 6,000, about 6,000, to several millions. Okay, so we can join, we can chain, we can bond thousands of amino acids to form big and bigger proteins. Okay, so those amino acids, we have said that they are 20 in our proteins. They can be grouped based on the different side chain. Okay, of course, the only part that changes is the side chain. Okay, so we can classify them in four different groups: non-polar or hydrophobic, and uncharged. Of course, let's say that all non-polar amino acids are uncharged, at least in when they are in proteins. Polar or hydrophilic amino acids can be uncharged or charged. So we can further divide polar or hydrophilic amino acids in 3 groups, which are the polar uncharged ones and the 2 different groups of polar charged ones. Of course, if they are charged, they can have a negative charge if they are acidic, or a positive charge if they are basic. Of course, the final structure of a protein depends practically totally from the kind of amino acids that are connected one to the other, and that form its basic structure. Okay. Every amino acid, according to this classification, produces some kind of effect in the structure of the final protein. And also, if we have some groups of amino acids together, they can form specific structure in the protein. Okay. Okay. So here we can see here we have side chain that are basically hydrocarbon chains or aromatic rings or aliphatic rings. In this case, we have sulfoether, but all of these are basically hydrocarbons, and thus they are quite nonpolar, quite lipophilic or hydrophobic. The polar amino acids, uncharged ones, are these. Here you can see that we can have alcoholic groups, amide groups, CONH2. This is an amide. Thiol group or phenol group. Okay, all of these include this part, the amino, or better, amide group, alcoholic group, or thiol group. All of these are quite polar groups, so the side chain becomes polar. Okay, so these are polar amino acids. And then we have just a few acidic or basic amino acids. Here you can see the acidic group, COOH, of aspartic and glutamic acid, and the basic groups, amino, urea, and histidine group. Okay, so sorry, histamine group. Histidine is the name of the amino acid. So all of these contain the amino group, which is basic. All of these contain the carboxylic group, which is acid. Okay. Okay. How are proteins formed? It is a simple, let's say, reaction between the carboxylic group of one amino acid and the amino group of the other acid. This reaction can be called condensation because it happens with the loss of a water molecule, and a so-called peptidic bond is formed. It is, of course, a normal amide group, so it's an amide bond, but in this case, the amide is called peptide, so peptidic bond. So if you can imagine that at this end, you can attach a lot of other amino acids. At this end, you can attach also a lot of other amino acids. And so you can form a chain as long as you want. And this chain, as you can see here, doesn't contain any more amino or carboxylic group except at either end of the molecule. Okay, at one end we will have an amino acid with a free amino group, and the other end we will have an amino acid with a free carboxylic group. But in between, all amino acids chained in the protein structure will not have the amino or the carboxylic groups free apart from the side chain. Okay, so only the side chain give to the molecule different properties, because the main, let's say, amino and carboxylic groups are, let's say, bonded in the peptidic bonds, so they are not free anymore. Okay. So a lot of amino acid bonded together with peptidic bond form a specific chain, a very long chain of as many amino acids as needed. And this chain, according to the different kinds of amino acid included in the chain, will form so-called secondary structure. The primary structure is the simple sequence of amino acids. Specific sequences of amino acids within the primary structure will form secondary structures. Here you can see that there are two main kinds of secondary structures, which are an helix here and here, and a sheet. It means a linear part of the molecule, which is folded in two to form a linear, more or less linear sheet. Okay, and all these structures can repeat many times along the molecule, forming a three-dimensional structure, which is called the tertiary structure. Okay, and at this point, when we obtain a three-dimensional molecule with several different features over the surface, over the internal part, that the function of the protein becomes effective. Okay, so only when the protein can keep this tertiary structure, all the features on the external and internal parts, all the small holes or the groups that are going out from the molecule, can the protein work properly. Okay. Okay, so we have talked about the fact that it is the tertiary structure that produces the function. Which kind of function have proteins? A lot of different functions. One of the most important one is the structural function. For example, skin, bone, that are important for the body structure, contain a specific protein that is called collagen. Another very important function is catalytic function. In every cell we have a lot of different proteins. They have a specific name. They're called enzymes, but they are still proteins that have the specific function to catalyze reaction within the cell. Okay, as you may remember, catalysis means lowering the energy threshold for a reaction. Okay, so enzymes are proteins that have the specific function of making reaction easier. Okay, to make them happen using a lower amount of energy. Also, specific proteins are have the specific function of allowing movement, of course, in muscle. You may remember that two specific proteins are mainly involved in the muscle movement, actin and myosin. So they are just two, but very important for the body structure and to movement. Nutrition. some proteins are, let's say, a reservoir of nutritional elements. Okay, so for example, in milk, human or cow milk, we have a protein which is called casein, and casein has no specific function other than providing amino acids for the baby, let's say. So it is a specific nutritional function, but not structural or something else, okay? So it is just in milk to provide specific amino acids to the baby, okay? And also, you may remember, I talked about it before when talking about the cell membrane, also a transport function, okay? Hydrophilic compounds cannot pass the membrane unless they are transported. The transport structure within the membrane are proteins, okay? So in the, let's say, submerged in the membrane, we can find a lot of different proteins that can transport different compounds from the external part to the internal part of the cell, and also vice versa, okay? Many substances that should be eliminated from the cells are transported by proteins through the membrane. For example, okay, this is a different kind of transport. Hemoglobin, it is the molecule that transports oxygen to every body cell. It is contained into red blood cells. And this is another kind of transport, but in this case, the protein has just the function of bonding itself to the to oxygen and to release oxygen once the red blood cell arrives to the tissues. Some proteins also have a regulatory function. They can regulate different cell function, and those proteins are called hormones. Specific proteins called antibodies have a protection function. They can bind specific parts of the surface of bacteria or virus and viruses, and they can inactivate them or mark them for destruction. Okay, those are antibodies. Other proteins can store substances, store important substances. For example, iron is a very important element for our body, and it is stored in the liver within a protein. This protein is called ferritin, or also, sorry, okay, the word slips me, not a problem. Copper, okay, the metal copper is also transported and stored in the liver by another protein, which is called ceruloplasmin, and so on and so forth. Also, today is a bad day for my language. Cholesterol. Also, cholesterol is transported within the body, conjugated to proteins. And also a regulation function. In this case, protein can, let's say, transport information. For example, rhodopsin is a protein that changes its structure if it is struck by light. of course, this is found in the eye, and it is one of the mechanisms that allows us to see, that enables vision. The change of structure of rhodopsin, which is a protein, when it is struck from light. Okay, this is in more detail the function of enzymes. So enzymes, as I said, are proteins, and they have the function of facilitating reaction. Okay, so normally here in the graph you can see that we start with reactants. They have, let's say, a specific energy level, and let's say by necessity, the product should have a lower energy level, because if the reaction has to be spontaneous, has to happen, the products must have a lower level of energy. So between the two levels is some sort of barrier, of energy barrier, okay, that has to be overcome to produce the products. So in order to have the product, we have to take our reactants and give them energy in order to have the products. So the specific function of enzymes is to lower this barrier. Here you can see what happens when enzymes are involved. You have a much lower level of energy to give to the compounds in order to have the products. And so the reaction is much easier to happen, it's much faster. And what the enzymes usually do is to take, let's say, for example, two compounds and bind them, not very strongly, to themselves, and to orient, to, let's say, change the position of the two reactants so that they can react very easily. And so we have the product. So enzymes usually have specific structure. You can see here this structure here. It is like an hole of some kind that can accommodate only a specific kind of chemical structure. And so they are quite specific. They can only facilitate reaction involving this kind of chemical compound. They are not extremely specific, so they are not making reaction involving just one compound, but usually one class of compounds. Okay, so let's say that for reaction involving molecules like cholesterol, we will have enzymes that will not bind just cholesterol, but cholesterol and all other compounds with similar structure, which can include, for example, testosterone, estrogen, and so on and so forth. Okay. So this compound, which has a specific structure that can enter the enzyme and involve the enzyme in the reaction, is called the substrate. Okay, so each enzyme has a specific substrate, which is specifically, let's say, attracted in some way to the enzyme, and the substrate is not a single kind of molecule, but it is a class of molecules. Okay, here there's a list of different enzymes, but I don't think it's very useful to study or to remember those names. It's just a list in order to show you that almost no reaction happens in the cell without the action of enzymes. Okay, so we have classes of enzymes. These are, let's say, broad classes of enzymes. Oxidoreductases. All enzymes that catalyze redox reaction are called oxidoreductases. Or transferases. They transfer groups. Okay, so we will have different subclasses of transferases. For example, methyl transferases, amino transferases, and so on and so forth, according to the specific group they are able to transfer. Hydrolases make hydrolysis reaction happen, and so on and so forth. Okay, no need to enter in much detail, just to understand these are classes, and within each classes we have several different enzymes specific for different substrates. Enzymes can be very useful in industries because they can transform, let's say, more or less automatically, several kinds of compounds in a useful way for us, for humans. And they do this without producing pollutants, okay? Because they are, let's say, biological compounds. So we don't need much extraneous, much, let's say, toxic compounds that come, for example, from oil and so on. They do it by themselves and don't produce many polluting agents. So, for example, we can add lactase to ice cream in order to prevent crystallization of sugar when it is freezed, when it is frozen. So the ice cream stays creamy, okay, instead of being, let's say, crunchy. Or, for example, papain, it destroys the structure of meat, of some meat proteins, so meat becomes more soft and tender. So, of course, in this it can be useful, and so on and so forth. Okay, so as you have seen, proteins are very complicated, big molecules with a lot of different properties, a lot of different function within living beings. Now we see another kind of molecules, very important molecules, carbohydrates. Carbohydrates are also called sugars. Just like for proteins, we have the amino acids. They are monomers, and then they produce proteins, which are polymers. Here we have monosaccharides, and this is an example, glucose, the most important sugar in our body. And glucose, as you can see, is a molecule containing 1, 2, 3, 4, 5, 6 carbon molecules. And each molecule is connected to one hydroxyl group. Here the hydroxyl group has cyclized the molecule. And here we have another hydroxyl. So every carbon in the molecule is connected to an oxygen, and in particular to an hydroxyl group. So these are called carbohydrates, meaning carbon and water, because the OH group comes from water. And this is a monosaccharide, just one unit of sugar, one molecule by itself. But sugar molecules can bind together through this oxygen group, this hydroxyl group, to form long chains. In this case, you can see here that this alcoholic oxygen has bonded this one in another identical molecule. Okay, so two sugar connected together are called a disaccharide, monosaccharide, disaccharide. In this case, this is lactose, but it is the sugar that is found in milk that can be, let's say, a bit toxic for some people. And so we have the high digeribility milk. It is quite common those days, and it is simple milk where lactose has been broken down. This bond has been broken to form the two monosaccharides, and the two monosaccharides alone by themselves are not toxic for people intolerant to lactose. And we can go on adding, bonding more and more and more sugar molecules to form a polysaccharide. For example, cellulose. Cellulose is the basic building block of all plant structures. The plant world is built from cellulose. Okay. Also, from plants, we can produce paper, and paper is made from cellulose. In animals, the most important polysaccharides is probably glycogen. And glycogen is produced in the liver, and it serves as a sugar storage structure. Okay, so there's not much to say about sugar, apart from the fact that they are basically our most important source of energy. They are used by mitochondria, we have seen before, to release energy that can be used by the cell. But they can also bond to proteins to form glycoproteins. And glycoproteins have different functions from the protein from which we started. Okay, so a protein by itself has some function, but attaching polysaccharide chains to a protein, its function is modified. Okay, so we also have glycoprotein. Okay, I think for the second hour that's enough. So we can stop here, take a break. No, not at all. This is just to give you an overview of which is the structure, because in the following we will see, when we talk about the toxic properties of molecules, we need to understand how do they interact with our cells, with structures in our cells, and with those macromolecules like proteins, polysaccharides, lipids, and DNA, and so on. Okay, so I need to explain the structure, but of course you don't need to remember the specific structure of the molecules, all the carbons, oxygens, and so on and so forth. Absolutely not. Okay, I mean, of course you have to recognize, okay, an amino acid. Okay, if I show you this formula, you should understand, you should remember that this is an amino acid because it has an amino group and an acid connected by a single carbon. And if I show you this structure, you should understand, you should remember that this is a sugar and this is a polysaccharide. Okay, this is what you need to know, okay?
Okay, thank you.
You're welcome. Okay, so we can stop and take a break and come back in 10 minutes. If there's any more question, please write it down in the chat, okay? Thank you very much. Hi. Here I am again. Okay. So I don't see any questions in the chat, so we can go on with the next important biomolecules that are lipids. Lipids, in a macro way, are divided into two main groups: fats, which are solid, and oils, which are liquid. Most fats and oils are composed of triglycerides. Just like the name says, we start from glycerin or glycerol here, and we attach three chains, three fatty acid chains. A fatty acid is simply a long aliphatic chain, a long hydrocarbon chain, linear, connected to a carboxylic acid. So it is this chain made from 16, 17, 20 carbons, and at one end we have a carboxylic group, an acidic group, COOH, and this acidic group is bonded to the oxygen group, the alcohol group of glycerol. You can see here that the glycerol has 3 carbon atoms, and each carbon atom has an alcoholic group. So each alcoholic group can be esterified. This means that we create an ester here, COOR. This is the typical ester group, is esterified with a fatty acid. So an acid reacts with an alcohol to produce an ester, and here we have 3 alcohols, so a triglyceride. This is the most usual structure, but we also have different lipids. For example, cholesterol, it has a very different molecule, but the main thing is that it is hydrophobic. It is fatty molecules. Some hormones and some vitamins have this kind of structure, and all of them, just like all lipids, the definition, let's say, of lipid is that they have to be very hydrophobic, okay, or lipophilic. Lipophilic means similar to lipids, okay. So this is definition. Lipids are very important from a toxicological point of view, because, as I said before, many toxicants are soluble in lipids. And we know that this kind of molecule, triglycerides, are exactly what constitutes, what makes up the cell membrane. So everything that is toxic and lipid soluble, lipophilic, can interact with the triglycerides in the cell membrane and pass the cell membrane. Okay? And from a macroscopic point of view, you know that we have fat tissues in our bodies. We have a lot of small fat tissues under the skin, all over the body, and we have some specialized tissue, fat tissue, over our guts. Everyone has more or less fat over the guts, but this is not important. And these tissues is specifically interested when we are exposed to a toxic compound, of course, because if it is a lipophilic toxic compound, it will accumulate. It is very attracted by our lipid tissues, and it will accumulate in our fat tissue. Okay, the last very important structure, the last very important molecule, macromolecule in this case, in the cell is nucleic acid, or better, nucleic acids. We have two main kinds of nucleic acids. They are called DNA and RNA. I mean, of course, everyone knows RNA nowadays because of the vaccines made from this kind of molecule. COVID vaccine, obviously. DNA molecules are macromolecules, and they are polymer of monomers that are, let's say, quite complicated. The basic building block of DNA are nitrogen-containing bases. We have only four kinds of nitrogen-containing bases in the DNA, and four which are mostly the same in RNA. The only difference is that in the DNA we have adenine, guanine, cytosine, and thymine. In the RNA, thymine is changed to uracil, but it is very similar, okay? So we just have four nitrogen-containing bases. Each nitrogen base is bonded to a sugar, which is the oxyribose, or to be more precise, 2-deoxy-D-ribofuranose. But it is not a problem, it's not important. We call it, since it is called deoxyribonucleic, we call it simply deoxyribose. And connected to another position of the deoxyribose molecule, we have a phosphoric acid molecule, okay? This is the building block of DNA. So when we bond, for example, a nitrogen-containing base like adenine with the sugar, the deoxyribose, we obtain a nucleoside. So this is a nucleoside, nitrogen-containing base plus sugar. And when we connect, okay, here you can see that this is the bond between the base and the sugar, and in another position here, you can connect a phosphate group. And in this case, we have the nucleotide. So nucleoside, nucleotide. The nucleotide is the basic building block of DNA. And when we connect a lot of nucleotide together, we obtain a long chain of DNA. If this sugar is ribose instead of the deoxyribose, we obtain chains of RNA. Typically, two DNA chains are coupled together and kept together by coupling corresponding bases. Here you can see in different color the different nitrogen-containing bases. Here you can see the building block, the base, the sugar, and phosphate. And you can see that this OH of the sugar is connected to the phosphate of the following nucleotide, okay? Here you have a nucleotide, and the sugar here, the sugar here is bonded to the phosphate of the following nucleotide, and so on, and so on, and so on. So this, on the left, is a DNA chain, and this on the right is another DNA chain. And the two chains are kept together by weak interactions. These are not covalent bonds, they are weak interactions between one base and another base. In particular, adenine always couples with thymine, and guanine always couples to cytosine. Here you can see guanine and cytosine. So this is like a zip that keeps, or Velcro, that keeps the two DNA chains together. Of course, just one or two bases coupled in this way, since these are very weak interactions, will not keep the two molecules together. But we have thousands of nucleotides in DNA, and so those thousands of nucleotides will keep the two chains together through those thousands and thousands of weak interactions. But this also means that when needed, we can open and keep the two chains apart in order to use the DNA to produce whatever you want in the cell. Or we can open only part. Of course, DNA is never used all together, but we can open specific part of the DNA, because these are quite easy to open one by one, and use the open part of the DNA to produce whatever we want to produce in the cell. This is the macro structure of DNA. Here you can see again the two chains where A, T, G, C are always coupled together, okay? Always T with A and C with G, or vice versa, G with C and A with T. And together they form this double helix that is contained within the nucleus. And the function of DNA is to provide blueprints for producing proteins. All proteins in the cell are produced by from the blueprint written within the DNA. So these sequences of nucleotides are a code which encodes for the production of a specific protein. So specific part of the DNA will be used by the cell as a blueprint to produce specific proteins. But the DNA can only be used when it is open, it is unraveled. And so only the part that is open can be used. So the cell can regulate which protein it wants to produce by opening different sequences of the DNA. Okay. I think this is everything for regarding the basic principles of biochemistry. Please, if there's any question regarding everything we've seen today on proteins, sugars, and lipids. Just a moment. Okay, this one. Okay. No questions? Everything's clear? Okay. Now we have seen the most important structures in our cell. in our cells, the most important molecules, in particular big molecules, for many functions in our body, in our cells. Now we can start taking a look at metabolic processes. Metabolic processes are complex sequences of chemical reactions involving those biological molecules we have seen before, that the cell and our body use to perform all needed function to keep us living and working and functioning in general, okay? In particular, metabolic processes are those processes involving the intake of substances into the body, their breaking down into smaller molecules that can be absorbed through the intestine. Okay, so we mainly introduce food and water, drinks, into our body through the mouth. They are digested. It means broken down into smaller molecules. And when the food and drinks are broken down into molecules, small molecules, are absorbed through the intestine. Then the small molecules go into the bloodstream, and they are transported to the liver, where they are modified if necessary, and from the liver to the rest of the body. And in the rest of the body, and also in the liver, the small molecules undergo the opposite process than digestion. It means that small molecules can be linked together to form bigger molecules, just like in the production of proteins, lipids, and DNA. Okay. Also, we have the need for oxygen. So the intake of oxygen happens through the nose or the mouth. It goes in the lungs, where oxygen is brought into blood, brought to all the body, where the essential process of cellular respiration happens. We have seen it before, okay, where the sugar and other kinds of substances are further broken down to produce, to release energy, okay? And then this energy release produces carbon dioxide, which from the blood goes to the lungs and then out of the nose in the environment. Okay, so this is the main overview of metabolic processes. Okay, so we have intake of food, drink, water mainly, broken down. We break down molecules, transport to the tissues, use of these small molecules, either for building or for producing energy, and also the intake of oxygen to produce energy, and the exhaust, let's say, the elimination of carbon dioxide. Okay. So metabolic processes, by and large, can be divided into two very big classes of processes. And they are called anabolic processes, or anabolism, and catabolic processes, or catabolism, where ana and kata are two Greek words, prefixes, that mean, up and down, more or less. Okay. So up means building something. So when we talk about anabolic processes, we mean that we use small molecules in order to produce larger molecules. And this is a process that requires energy, okay? We have to form new bonds, new chemical bonds, and this requires energy. On the opposite side, we have catabolism. Kata means down. So larger molecules are broken down into their small components, and possibly small molecules can also be broken down into smaller molecules still to release energy. And as you may imagine, the energy released by catabolism is used in anabolism to produce larger molecules as needed. Okay? So we have an example of anabolism. Anabolism means producing large molecules, sorry. And this is an example. When we link together two or more sugar carbohydrate molecules to produce the saccharide or a polysaccharide, we have an anabolic process. We take small molecules, and if the reaction goes in this direction, okay, so from two or more small molecules, small sugar molecules, we produce first a disaccharide, then a trisaccharide, then a polysaccharide. And here, as you can see, two alcoholic groups are condensed into something like an ether with the release of water, because here we lose two hydrogens and one oxygen that, of course, produce water. So this can also be thought of as a condensation reaction. When we say condensation, we mean that we have the loss of water. Okay. Another example, these are all reactions we have already seen when we were talking about important molecules, okay? This is regarding polysaccharide. This is regarding triglycerides or lipids, okay? So when we take glycerol and make it react with fatty acids, we obtain a triglyceride molecule. And here you can see the condensation reaction will release one water molecule for each fatty acid. So 3 water molecules. Again, this is anabolism, okay? And also, when we look at proteins, when we condensate amino acid to produce the peptide bond, again, we have the loss of water, okay? So, as you can see, in some way, all these processes are similar, okay? A condensation process, anabolic process that produce larger molecules. And in a way, many catabolism reaction are simply the opposite reaction, or better, the same reaction going in the opposite direction. Here you can see the images are exactly the same I showed you before, but as before, they have a double arrow between them, meaning that this is an equilibrium, okay? All these are equilibria. And if we start from the simple molecules producing the complex one, of course, the equilibrium is shifted to the right. And in this case, if the equilibrium is shifted to the left, we will have a catabolic reaction starting from a big molecule, a protein, polysaccharide, triglyceride. This reaction needs water instead of producing water, needs water in order to destroy, to break down bonds and to form smaller molecules. So these are hydrolysis reactions. When we use water to break bonds, we call it hydrolysis, okay? It is the reverse of the condensation or dehydration reaction. Okay? Okay, this is anabolism and catabolism up to the level of the single molecule. Here we have single sugars, single glycerol and fatty acid, single amino acids. But we also can have metabolic pathways that can involve single molecules, which are broken down to producing even smaller molecules. And we can have, in particular, pathways leading to the release of energy. What is the meaning of pathways? Pathways is a sequence of reactions. Sorry, I forgot to mention that all of these reactions, both the anabolic reactions, and the catabolic reactions, are mediated by enzymes. Okay, so we will have specific enzymes that catalyze anabolic reaction and enzymes that catalyze catabolic reactions. In line of principle, since this is an equilibrium, the same enzyme can work both ways. Okay, so the same, according to the conditions, the same enzyme can catalyze the anabolic or the catabolic reaction. So since it is is catalytic, it can facilitate the reaction in both directions. Okay, but we will see that several times we need different enzymes because the anabolic reaction needs energy, and so the enzymes must accommodate also the energetic part of the reaction. Okay, so usually we have different, but in line of principle, the same enzyme can catalyze both reaction or the reaction in both directions. Okay, so a metabolic pathway is a series of reactions that start from the first compound, let's say the complicated big molecule, and we have a series of enzymes, different enzymes, that can catalyze the production of different substrates. So we start from a molecule, and the first enzyme, let's say enzyme A, will transform this substrate in another compound, let's call it substrate 2, which is the substrate of a different enzyme that takes substrate 2 and transforms it into substrate 3, and so on and so forth, until we obtain the desired product. This can be an anabolic pathway, where we take, for example, amino acids, and at the end we obtain protein, but it can be any kind of reaction, really, also catabolic reaction, but the most important pathways are those that produce some, not the macromolecules like proteins, DNA, but that produce, for example, hormones and so on. Here we have different enzymes that attach to the starting molecule different functional groups until we end with the desired product. And we have also a strict control over this series of reaction, and this control is called negative feedback inhibition. What does this mean? It means that we have some other protein or some site on the first enzyme of the chain that can bind the product. And this binding of the product to a protein or to the first enzyme inactivates the enzyme. So if the cell is producing this red product, let's call it, it will take substrate 1 all along the chain with different enzymes to obtain the product. The product, in turn, will accumulate because it is continually produced by all those enzymes. But when a high amount of product is obtained, some of this product will manage, let's say, to bind to enzyme A. And it will stop working. Enzyme A will stop working. So we will break the chain and we will not produce anymore this product. So in this way, we can control the amount of this product in the cell. Of course, if this product is brought out from the cell, if it is degraded in the cell, it will stop binding the enzyme A, and so it will start working again, and again starting the production of this compound. Okay, so this works for almost all compounds, all substances in our cells. We almost always have this negative feedback control over the production of substances in the cell. And you can see that the pathway can be quite complicated. It can involve a lot of enzyme, of intermediate compound to produce the final one, but it can be controlled by just one step, which is the first enzyme of the chain, of course. So the control is relatively simple in comparison to the complication of the metabolic pathway.
Professor?
Yeah?
So the negative feedback is used to stop the production?
Yes. It is used exactly to stop production when enough product has been obtained. Okay? So a lot of product will accumulate, and some of it will stop enzyme A from working. And of course, this stops basically all the production of this compound. Okay?
Okay, thank you.
Of course, when we have just a small amount of product, it will not bind to the first enzyme, and so production will start again. Okay, so negative feedback is a mechanism of, let's say, synthesis block in some way. Okay, synthesis stop. Okay, so the next topic is the production, or better, the release of energy within the body. So it is a bit longer, and I think we should start it next time. We can finish here with the lesson, and I ask you if there's any question right now. No? No one else wants to ask something? If there are no questions, I think we can stop, and we will come back on next Thursday, I think, yeah, at 9. Okay, someone maybe is writing. No? Well, okay. If there's nothing else to say and to ask me, I think it's over. Thank you, and see you next Thursday. Bye-bye.
Thank you.
Thank you.
Bye.
Thank you.
Thank you. Bye.